Okay, hello. Welcome to my talk. You don't introduce me?
So, it's a pleasure to have Marko giving a talk about
graph operands and graph complexes. Exactly. So I was supposed to prove that zero homology of graph complex, I will explain what it is GRT 1 with Grothendieck-Teichmüller Lie algebra. And I will go in this direction, but I think there's no way I finish. Therefore, my title will be Graph operands and graph complexes. Okay, so first, okay, so this maybe. First, some repetition from the last time. We introduced operand Lie. It was generated by the generator, this one. Or we can draw it like this. It's first input, first output, and this. Or since there is only one generator, we can omit any sign here. And there are relations. I can do it xy equals minus yx. Or if I draw 1 equals minus 2, 1. And Jacobi identity x, y, z plus y, z, x plus z, x, y equals 0. Or I can draw it like this, but I won't. Okay. Next operand, which was introduced last time, was Gerstenhaber operand. So Ricardo introduced it. It's signed Ger, but I will call it E2 because it was called E2 in this paper. Okay, well, everything what I'm talking about is based on the paper of Thomas Villwaher. This where he proved that graph complex is quasi homology of graph complex is GRT. Paper is called Kontsevich graph complex and Grothendieck-Teichmüller Lie algebra. Okay, these two means something. In general, there is En, but I will work only with E2, therefore I can call it just E. And E means E2. And also this GC is actually GC2, but since I will talk only about 2, I call it only GC. So this Gerstenhaber E2 or E is generated by two generators, Lie, I can call it Lie, and wedge product. Or I draw it like this. Now I need to write down what is this. And generators for Lie are the same or almost the same. So this operand is graded operand. And we can think of it as differential graded operands where differential is 0 in this case. And this is of degree -1 and this is of degree 0. Now this anti-symmetry is not super trivial. It's x, y equals minus -1 to the degree of x, degree of y, yx. I thought, okay. In most of the cases, you can forget about this sign. Sign is sum, but just to know that it's not always minus in this case. And there is Jacobi also signed, plus minus, okay. Plus minus, plus minus, plus minus, something. Yeah. Graded Lie algebra. But where Lie bracket is of degree -1. Lie bracket can be of degree 0, then we will not have that. But if Lie bracket is of degree -1, we have to be careful with these signs. Okay, so this is first relation. This now is second relation. I won't repeat. And this is commutative and associative. So third relation is 1, 2 equal to 1. Fourth relation this, where these are edges. So it's clear. And fifth relation is something what explains the relation between two of them. It's x wedge y z equals x wedge y z plus x z wedge y. I hope there are no signs. Maybe it's plus minus. I don't know. Okay, so let's come back to this Lie and try to figure out how does the basis of Lie n look like? So Lie n is a vector space of Lie operad in arity n. So in arity n, we have inputs.
This was denoted D sub n in your operad.
No, these are inputs of an Lie.
Okay, that's okay.
This n is not a vector space. N is a natural number. So Lie n is the n. Yes. When I was writing m.
Yeah. Okay.
So this is just operad element of Lie operad of arity n. So this here, for example, this generator is in Lie 2. Okay, so Lie n has n inputs. I can call it x1, x2 to xn. And we can show that this is the basis. We can always start with xn, and then comes xi1, close, xi2, close, xin-1, close. Okay, using this and these relations, we can every element in here write through basis of this kind. So we can always put one chosen, I choose the last one, into the deepest into the all brackets, and then put like this. So do you believe me, or I think it's clear. So just if xn.
Maybe you can just give a short example with n equals 3.
Okay, let's hear. So I mean, if x, y, and z are something longer here, and xn is inside here, then we express this in terms of these two. We always want to put xn deeper into the brackets. And we do it as we can do, and then we will get this.
I'm not sure I'm understanding. So the x1, xn, they are elements of a free algebra, or I mean, are they?
No, they are just inputs of the operand.
So
I can.
they're indices of the legs of the.
Yeah, so if you
Yes.
count it as a tree, it's like the ways to put the 1, 2, 3, and that are down there, right?
Yes. So
Because
this
you can just
in
put
like a
it
tree
right?
will look like this.
You want that xn has the deepest height in the tree.
Yes.
So you
So this will be n, nth input, and here something, some permutation.
The axis like represent where does the first
Okay,
input go,
okay,
where does
okay,
the second input go.
Okay, so you have
the
to-
relations to give an order.
and also to put to rewrite so that it's include, because it include other ways to write it, right? Not order from the left. You could have.
I can have like this.
Yeah, so
Yes, but using this relation, everything can be written in this form.
Yeah, and you can choose.
And I can choose that this is n.
You can write the sum of guys.
But this is the basis.
Therefore, it's dimension minus.
Exactly. That's what I need. Dimension of Lie n is n minus 1 factorial. Okay. And now look here what we do to this E. So E, using this relation, I can put all wedge products outside. You believe? And then, so every element can be written as something wedge, something wedge, and so on. So I put all wedges outside, and these are Lie words. And now I can write this in this form, such that the maximum here put on the first. So I can call it x1, 1, x1, 2, x1, something, whatever. Wedge, let's call this x2, 1, x2, 2, wedge, and so on. Such that this x ki, sk1 is maximum of x k1, x k2, and so on. Such that this one is maximum among these, this one is maximum among these, and so on. And since this commutes, I can also arrange it as such that x1, 1 is smaller than x2, 1 is smaller than, and so on. Such that this one is smaller than this one, and so on. Now, when I arrange, and this will be the basis of En. And now, when I arrange it like this permutation, so I just list these numbers. And from these numbers, I can reconstruct how does this look like. Just I found the maximum, and from the maximum till the end will be one Lie word. And then I found another maximum of the rest, and from that maximum till this end will be another, and so on. So there is bijection between these bases and permutations of n. Okay? Okay. So do you believe me that everything here can be written as a sum of elements of this form?
Everything was fine until the last sentence.
Okay. Now when I have this form, I just pick, these are numbers from 1 to n in some order. These are inputs. So if I just forget about the brackets and wedges, this is a permutation.
Yeah, but on the other hand, if you have another permutation, why do you get?
And if I, okay, so this is a permutation. So from this to permutation, it's clear how to get. Okay, and now I have permutation. 1, 4, 3, 5, 2, 6. 1, 2, 3, 4, 5. Okay. So because of this, x k1, the last one, will be the maximum of everything.
It would be just bigger than all the words which are.
So the maximum here, then I have maximum of this here, and I have maximum of this here, and I here. So this must be 1, wedge 4, 3, wedge 5, 2, wedge 6. Okay, so there's bijection. Therefore, dimension of En is n factorial. That's what I need. Okay. New operand called GRA or GRA. I cannot call them graphs because there will be another operand later which I will call graphs. So these operand I call GRA. So this operand looks like GRA n. GRA is, how should I call it? GRA. GRA n has n inputs, but inputs are here vertices. Vertex 1, vertex 2, vertex 3, and vertex 4, for example, is in graph 4. And I have edges which connect two vertices, for example, like this. So this is an element in graph and graph 4, exactly. And graph 4 is generated by elements of this kind. Of course, vertices are numbered. They will represent inputs. I will show later how composition works.
The action of S4 is permutation of the labels.
Yes. Yes, exactly.
With no minus signs.
No minus signs, no. In graph 2, no minus signs. I'm working in graph 2. But these edges are not completely distinguishable. So I will call them 1, 2, 3, 4, 5. But this will be minus if I change two of them. So if I now call this 1 and this 2, and still call this 3, this 4, and this 5. This will be equal to minus this. Okay, and if I now exchange two others, then it will again be this. I will most often omit these things. So I will omit this. Then this picture will represent element of Graham up to a sign. Sign will be not clear from the picture. Okay. Now, edges are of degree -1. This will again be differential graded opera. The differential is 0 again, but we have grading according to, we have grading such that edge is of degree -1. Because of these things, I cannot have multiple edges. Let's say I have this, and I have two edges between two vertices, but I can flip them and get minus, but it's the same graph. So since it's minus, then it's 0. Therefore, in graph, I cannot have multiple edges. What I can have are tadpoles. Tadpole is an edge which starts at the same vertex. But I will have two complexes. I will call the one where I allow tadpoles graph like this. This represents tadpole. And the one where I don't allow tadpoles will be just graph. And differential goes as you can maybe guess. One graph I put.
So you have to put another rule to eliminate the tadpoles like you did here by assigning some degree, or
No.
or you just say that.
Yeah, here I just say tadpoles are not allowed. Because a priori tests would be allowed. And so composition, graph, 1. Okay, 1. Composing to the slot J, another graph, is putting graph gamma prime into the vertex J and connecting all edges which were connected to vertex J in here, two vertices in here in all possible ways. For example, let's say this is gamma, and I want to put gamma prime, this thing in there, in slot 1. So gamma 1 gamma prime will be, so this was 2, 3, 4, edge here, 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 but here I put this. And now I connect this in all possible ways to these two. Here, plus this is the same if I put this here, plus if I put this both here, and plus if I change here. Okay, then this will be shifted. So this will be 1, 2, and this will no longer be 2, but 3, 4, 5. Okay. Do you get it?
So you don't connect. So I would say that.
Yes? Then you, what?
Nothing. Continue.
And then you connect both ends of the loop to all edges in all possible ways. For example, if I, including loops, yes. So to this loop will be this plus this plus this and plus, I mean, I should have two of these.
So that's the composition of the insertion of
I have to,
two into a loop.
yeah.
But they don't cancel out. These two upstairs.
I mean, they are zero in this case, if this,
Okay.
so let's say
But
this
the
doesn't
imagining is
exist.
something like this.
So sorry, could you write down what is this equal to?
Sorry?
Could
This is
Insertion of two vertices.
insertion in this, inserting into the loop. that
Without-
pole.
Without the edge connected.
Yeah, without the edge now, yes.
So Gra is not connected.
No, it doesn't need to be connected. Now do these two cancel out? I don't think. This is a bit small. Okay. So this was okay, I'm finished with this. Okay. So now a bit of general story. If I have operand P, then I can define a vector space P to the power of S. I just did the notation. What is for n bigger or greater than 1, Pn to Sn.
Sorry, what is S?
S is a symmetric group acting on here.
No, there. Wait, I don't know. S is a letter. It's a number. It's a what? When you
No,
say
this is a group.
yeah, no,
S.
it's on the left. Okay.
This is just a notation.
Okay, this is
But you brought S with the buffer. It doesn't use the buffer. It doesn't use.
oh okay, okay, and this is co-invariance under the S.
Yes, these are invariants out to, under this section, so it's just forgetting the numbers on the inputs, on vertices in this case.
Yeah, invariance and coinvariance are the same in characteristics here.
Okay, and I denote it like this. So in my case, Gra S will be what I will call FGC, full graph complex. Yeah, it's just this operand when I forget the numbers on the vertices. In here, if I have something like this, I can have Lie algebra structure always on this here. Lie algebra structure looks like this. First, I define pre-Lie algebra structure. X pre-Lie y, where X and Y, okay, I should denote where are they. So this is, do you need this? Yeah, I don't have empty graph. I need this story only because of graphs, but this works in general. So when x is in Pn and y is in Pm, then x pre-Lie y will be, by definition, sum I goes to from 1 to n, x I put in ith slot y. So this is putting y in all slots of x. And you can see that this is a pre-Lie algebra. Pre-Lie algebra means that this relation holds. X, y, z minus x, y, z equals x, z, y minus x, z, y. Okay, do you believe me that this is pre-Lie algebra? Okay. Okay, I can show this if you want. Okay. So this I can this pre-Lie algebra structure also put on PS. So on, because I'm summing over all inputs, it's invariant on this. So I have pre-Lie algebra structure on PS. And also I have a Lie algebra structure on PS where Lie algebra x, y is just defined as x, y plus or minus yx, depending on the degree.
So if we're looking at the algebra structures as operands, what does it mean? Right? You have a Lie operand, right?
What does it mean?
Yeah, what does it mean to, I mean, in the operatic sense, to give the algebra structure to an operand?
First of all, that's not an operand, it's just a vector space because
P is a vector space.
no, P is an operand.
P is an operand, but if I put S, then it's not operand anymore, it's just a vector space. Or if P, if P was a graded, differential graded Lie operand, then this is a chain complex.
But this question made sense even without the reverse, right? You told you first build the
Yes, this pre-Lie algebra can be taught also on the operand.
I mean, to define everything you defined so far, you
So this makes sense also for the operands, and yes, you have Lie algebra, pre-Lie algebra, and therefore also Lie algebra structure on the operands.
If PS is a vector space, and what you can do is you can circ Lie with PS, then you get what the answer is.
No, but here the circ is not the circ we had before. Here the circ is just the composition
This
on.
is clear.
This is composition in P.
It's okay. We'll talk about it.
Okay, I need this only for graph. So what's on graph S? What is full graph complex? First I define this and then I take invariance. This is invariant under action of S. At the beginning, no, but yes, but I will not need the Lie algebra structure on this operand. I want Lie algebra structure on full graph complex. I want to talk about that. So I want Lie algebra structure here. So what is Lie algebra structure here? I had, let's again.
Sorry, here it's not a theorem, it's just a renaming. What?
No, this is just a renaming. This is definition. Sorry?
You define it on the left-hand side, on the right-hand side, you state zero equalities people.
Yes, exactly. Okay, so this with this, what will this be? I first put this into all these vertices, and then I put this into these two vertices. Okay, it will be too long, so.
Oh, are you using the fact that the bracket of this guy on the right is a one-cut element?
Not now.
Not now.
Okay, I could. No, this doesn't exist. But okay. So do you understand what I will do here? So this is, I put this here and connect these two in all possible ways. Then I put this here and connect these three in all possible ways. Then I put this here and connect. Then I put this here and connect. And then I put all this here and connect, all this here and connect, and all this here and connect.
So how many symbols do you have?
So with the minus.
24.
Manual.
He's not going to do it,
I would say that no one cares answer is widely accepted here.
So it's 34. I think it's a sum of 34 sets.
Okay. Okay, so you get it. Okay, very nice. And okay, this was a differential graded operand. Therefore, this is differential graded. This is chain complex simply, but differential here was 0, remember? So differential here, basis differential is 0. But I don't want 0, I want to shift it by Marko-Tan element. And Yael is very happy. So what's Marko-Tan element? In any L graded, degree graded Lie algebra, and alpha in L is Marko-Tan if this holds, if differential alpha plus 1/2 alpha alpha is 0. And alpha has to be of degree 1, you know? And since alpha is of degree 1, this is not 0.
But when you say delta, here it's the differential, but there is no differential.
In this case, there is no differential. This is in general.
Sorry,
This is general story, but in our story, this is not, because differential is 0. This. And if this holds, then there exists another differential, which is delta plus multiplication with alpha. And now I want to find the Marko-Tan element here and shift my 0 differential to something really what exists. Sorry?
The name is
Twist. Didn't I say twist? Shift. Ah, sorry. Twist. Yeah. Okay. So Marko-Tan element here will be this one. No, this formula has to hold. No. This is definition. Alpha of degree 1 is Marko-Tan if this is true.
But I think there's only one element of degree 1. Because what's the degree? The degree is number of edges, right?
Yes, but this is also
This is also of degree 1, right?
this is also degree 1. It doesn't need to be connected.
Yeah, but then
And the tadpole is also degree 1. Actually, I think this is also Mercatan element. We can make differential with this.
And if you add guys on the right, it changed the adaptation or? Okay, that's okay.
Yeah, because now if I multiply this instead of this, I'm putting also here. This is different graph than this.
But when you put the one on the right, you basically don't change anything, right? If you have just one vertex, I think that add of a one vertex is 0 because you plug one vertex in any vertex, so you don't change anything. And on the other side, on the other direction, you plug the whole graph into one vertex, you don't change anything. So you do something minus itself is 0. Yes. So I guess they define the same differential. So actually, there's only one differential except the tadpole.
Okay, I was wrong a bit. So here there are some degree shifts. To be precise, I don't want to lie to you. So this is not precise definition. So full graph complex is gra n, but shifted by 2, 1 minus n. Sn. This in particular means that I say, so I take, this only matters the degree. I take degree of element here and I shift by this, and then I get degree here. Therefore, degree of this is -1 from the edge plus 2. Actually, if I'm shifting, then it's minus 2, 1 minus 2. What is -1? What's 1? And so this is not of degree 1. I'm sorry. This is of degree. So what this means? This means that actually edges are of degree 1, -1, and vertices are of degree 2. And at the end, everything shifts by 2. So degree of this is 2, 4, 6, minus 2, 4, minus 1, 3. Degree of this is 3.
And so you're saying that with the difference between the number of edges and circles, you could have other guys with degree 1.
Yes. So this, okay, this is 0, but this is of degree 1.
So I guess
Again.
This is the shift you need to do to make the bracket to have degree what? Degree 0? What degree does the bracket have? It's a degree 0 Lie bracket?
No, it's degree -1. Or
you
or-
make this later a Gerstenhaber algebra, right?
okay, I'm not sure. We can check.
You just want to define a complex, so you just need the Grothendieck algebra. So I guess the bracket is degree 0. Here the point is just to get to the differential.
Then the bracket should be okay.
Yes, I think the bracket here is degree 0.
But what do you know why there's the shift on the left?
Because otherwise the bracket wouldn't have degree 0, right? If it has degree 0 with
I want this to be of degree 1. I want this to be of degree 1.
Yeah, but you could, from the start, if you just had by grading by the edges, it would also be of degree 1. So there's some.
Actually, it would be -1. So, in general, this is 2 here. I don't write this 2. But if we put n here, then this is not 2 but n. And edge is not, degree of an edge is not -1 but 1 minus n. And that's essentially the only difference between these complexes. Yes?
Can I ask you something? Maybe I didn't understand the it's on the level of this
Okay. Yes.
So if you plug in alpha and alpha for x and y, and you have degree 1, isn't it then always 2?
No, because you remember, where is Lie? It was xy is minus 1 to x, y, yx. It was this.
So x is 0.
So
the
if
degree of x
if
is
degree are 1, then this is 1, 1, and I have plus.
I'm just looking at the top line of the board.
This.
Yes.
This is not completely, I mean, this probably goes here minus 1 to xy.
Oh, okay. So yeah, so it depends on.
Yeah, so I put plus minus not to bother with signs, but sign depends on the degrees of x and y.
So what you actually want for a monotone element is that already this x triangle x or alpha triangle alpha is 0.
I want this.
Yeah, exactly.
And if this doesn't exist, then I want this.
Yeah,
Equal.
turns out that
triangle alpha is 0.
Yes.
And that's a very geometric. Yeah. That's what you were saying before.
Yeah. Yes. Yes. Yeah. So you can check this is. Maybe we can check it. This. Okay. So it's enough to put this here. So. Yeah, if I want to be clear, I need to. But this is edge 1 and this is edge 2. If I want to be careful with signs. So this is edge 1, this is edge 2, and now I put this into the other. No, I'm putting this here. No. So if this is 1 and this is 2, and I put this here, then this is 1, and this is 2, and this is 1, and this is 2. And when I put this here, 2, and I put 1 like this, and 1 like this. And now.
And the order is always 1, 2, 3 of the vertices.
you don't care about the order.
I don't care it anymore.
Okay, then maybe
No, but.
then I guess all the graphs are the same, so it's 4 times.
Yes, but what I forgot here, that this is always 0. Why? Because if I call this 1 and this 2, this equals minus 2, 1, but these are the same graphs, so it's 0. The same story as when I showed that there are no multiple vertices. So whatever I get here, this is 0.
Plus another copy of 0.
Yeah, okay. Okay, and now maybe it will be interesting. No, it's 0 divided by 2. Okay, for example, if I have loops, this here is a loop, a tadpole. Okay, this is 0. You know already. This is also 0 because if I make symmetry over this, then I exchange these two edges and I get minus what's the same. So this is also 0. Here I can cross this symmetry change. It is exchanging this edge with this edge, this stay, so it's again 0. And this is not 0. This is not 0. So what you will get, that loops are not 0 if, now let's call V the number of edges is congruent to 1 mod 4, and it's equal to 0 otherwise. I can easily show it if it's odd. If it's even, then I can always find a symmetry such that I am exchanging odd number of edges. Either in this case, I can make symmetry like this, but for edges, yes. Changing odd number of, exchanging odd pairs of edges changes the sign. So here I will not do like this symmetry, but then I do like this symmetry, and I change this pair, and this pair, so it's 0. And if I have odd number of vertices, which is congruent to 3 mod 4, this symmetry, this here and here will be odd number of edges, so I will get again 0. Okay? So this will be important to know that among the loops, only these loops exist. Okay, now I'm using too much board. I define full graph complex con as some complex of full graph complex generated by connected graphs. Okay. I just take connected graphs and
It means generated because
actually it's not, graphs are not elements. Elements of the space are linear combinations of graphs.
So
Linearly generated by connected
So
graphs.
FGC con is just a subvector space
Yes.
of the operat, not a suboperat.
No, not suboperat. We forget about operats now. It's sub-Lie algebra.
FGC is not even an operat, right?
No, neither of them are operats here. So it's sub-Lie algebra. You can easily see that Lie structure preserves connectedness.
even an ideal, right? Because if you have something which is not connected and you plug in, no, sorry, forget.
Not necessary. Not necessary. Okay. So, and it's again complex, so you have differential. And symmetric product of vector space, we can define it to be this V tensor yacht S yacht. This is a symmetric product, and we can see that FGC is symmetric product of FGC con but with some shifts. You remember every graph had a shift of 2, so I have to subtract it and then add it at the end. Not important. Full graph complex is a symmetric product of connected. It just means that every graph is can be composed of connected graphs. And also this is true on homology. So homology of FGC is S plus of homology of FGC con with shift.
Differential D depending on the Marko element, right?
Sorry?
So H is with respect to the D depending on alpha.
Yes, but I chose all that alpha forever.
And it's a property that this adds some derivation with respect to the product of graphs. So that because the fact that it goes this is true also in homology is in fact the fact that the adds by derivation with respect to the
yes, exactly. So if I have two connected components in the graph, differential acts on the other, and on the one plus differential acts on the other. Yes. That's what. Yeah.
Symmetric algebra symmetric algebra is an exact function. Exact it commutes with homology. Tensor products commute with homology. Yeah, but here the point is that we have first defined D on the tensor product, so we have to check that the D.
Yes. So in fact, we have to check that the derivation of the whole thing is derivation of one part plus derivation of the other part. But it's clear. Okay, because of this, if we are interested in homology of full graph complex, we are actually investigating homology only here. So some side story, homology of graph complexes is not known. That's open problem. We know only some things, such that zero homology is GRT, and some other stuff, some computer calculations for small numbers, but in general, this homology of FGC is still unknown. That's why we are doing all this story.
And the guys you mentioned up there, they are in degree 0?
These?
Yeah.
Yes. Are they?
I don't know because
No.
You said it's -2 for every vertex and +1 for every.
Yes, so they're not.
So there's.
So we
they are not the sigma i's. They are not the generators of the GRT. Nothing to do with that.
no.
Okay. They are the one with the spikes. Okay.
They are much more complicated. Actually, we'll take this off. This is easy part of homology. Okay, now let's work only on this from now on. I will move them out now. So you will. I'm afraid I'm super slow. Now GC, graph complex. This is the nicest notation, so this will be important. is subcomplex of full graph complex connected, generated, linearly generated by graphs with vertices of valence greater than or equal to 3. All this story works for allowing and not allowing tadpoles. No.
That's how you get rid of all of them up there.
Yes, so think that there are two definitions, con with tadpoles and con without tadpoles, and here are two definitions with tadpoles and without tadpoles.
No, that's what I'm saying. You get rid of the one on the top.
Ah, loops.
Yeah.
Yes, okay. So first we need to show that it is a subcomplex. So if we, it's clearly sub-Lie algebra, but if we take a differential of graph here, we still get a graph here. But you can check it easily because if every vertex is of valence at least 3, differential will split it. So what differential means? Differential puts this inside, so it splits. So maybe I was supposed to explain this better. So what differential makes to the graph? If I have graph like this, differential on every vertex splits it, this vertex, and connects what was connected in all possible ways, for example, like this.
Yeah, but then it's not trivial over there.
Wait a bit. Okay, so differential splits and connects to each possible ways, but one is not allowed. So to connect everything to the one is not allowed because this will be cancelled by another part of the Lie algebra. So differential of a graph is this, which means putting this here, it's splitting, but putting this here will be this. So out of these splittings, one will be cancelled. So differential, what differential works? Differential splits every vertex and connects edges in all possible ways, but not in the way that all edges are connected to the one vertex. Because this one is cancelled by other part of this. So clearly differential cannot make one valent vertex. Clear. But it neither can make two valent vertex because if I have vertex, it will, as you were right, can split this and make something like this. But it will also split this and make something like this. And these two will cancel.
So the example there is not good, right?
Because yeah, the example is not in GC.
This example is not in GC, yeah, okay.
Yeah. Okay, so it was not clear for me a priori that this was a sub-Lie algebra, but it is for
Sub-Lie algebra, it's clear if you put something without degrees, without valences less than 3. In there, you cannot make valence less than 3.
maybe you can.
Ricardo asked whether this is a sub-Lie algebra. But it's clear because in Lie algebra, you take one graph
Of course, sorry. Yes.
and put in the vertex in the other. You cannot reduce.
Yes. Sorry.
The problem with differential is that this is not here.
Yeah, but that was.
So you would, for differential, you need to check it again.
Yeah,
It's an auto.
Sorry. Yeah.
Yeah. But my problem was this. I thought, well, since the differential is given by a Lie bracket, if it's a sub-Lie algebra, it's a subcomplex. But we're taking Lie bracket, it's something that's outside.
Exactly.
So it's okay.
So we need to check for this, but this is cancelled. Okay, so this had a number, I is here, and this new thing gets the biggest number, B, and this gets the biggest number, B. So these two are negative of each other because it's changing, so this sum is 0. They will always cancel. So in taking differential, you can also forget about splitting where only one edge is connected to one vertex. You can also forget about this because of this reason. So only splitting of this, which will matter, is this. And now all possible ways, but 2 here and 2 here.
So is there any physical motivation for considering algebra as a flat?
This next proposition is. So there is a proposition that homology is the same. So that we don't lose anything of homology if we turn to this graph complex. Yes, I'm just looking where I am. Proposition. First proposition. Very nice proposition. Homology of full graph complex connected with tadpoles is equal to homology full graph complex con without tadpoles, but plus K1. This is a basis field equals homology of GC plus big plus yacht greater than or equal to 1, yacht congruent to 1 mod 4, K2 minus yacht. You guess this comes from loops with yacht vertices. So loops you cannot kill. Loops are there and they form homology.
And sorry, I don't get what on the left, in the middle. What is what on the right? I mean,
This.
I mean, this sum here is compatible with the sums on the right, so meaning that.
Yes, this is the first element here.
Okay.
So this equals this plus here 3. Okay, I can put 3 and then this put outside. So this is this, and so this equals this.
Okay, so the idea is just that it's enough to compute.
Yes, this is Okay. Before proving, I will explain something about spectral sequences. So, are you familiar with spectral sequences? So, I don't need to talk about that. I need.
They are very technical and take a lot of time.
Yeah, so either you know them or you don't know them, and if you don't know them, it won't help.
Yeah.
Well, I think it would be nice if I say something. So just my, I write spectral sequences in maybe it will be useful. So I will write that. Let's try it. So C1, C2, C3. They are vector spaces, and if I have filtration, I can write it like C11, C21, C31, C12, C13, C23, C22, C32, and so on. And so this equals sum of these, this equals sum of these, this equals sum of these, and these differentials go like this, but can go down, but cannot go up. That's the whole story. Therefore, if I forget this, this is a subcomplex. If I forget this two, this down is a subcomplex. And if I have this,
Well, the diagonal ones, shouldn't they go two further, not just one further?
I write it like this, you can shift it. And this goes here. Oh, I mean, maybe you have in mind another setting.
Each time you go one sheet up, you not only move one down, but you also should move one to the right.
It depends on how you put, how you write it down.
Just saying the complex is filtered.
Ah, okay.
Okay, and this is the first sheet. Second sheet, this is differential. This is D0, let's say, and second sheet is homology of D0. So C11, let's say second sheet. C21, second sheet. And now I have differential. Now I don't have anything here. And now I can take differential along this diagonal and go to the third sheet and so on. And in some cases, which will be fulfilled in my always here, for example, if this is finite, if the filtration is finite, so I have just finite things here, or if every vector space here is finite dimensional, these two things I will need, then this spectral sequence converges to a homology of the original complex. So, and in most cases, it will be that here I get all zeros, and then I know that it's a cycle. Okay, this was super quick. I go to a proof of the proposition. Okay, first get rid of one valent things. If I have a graph and something one valent, maybe something else one valent, I call these antennas. Antennas.
Can points have antennas?
In which sense? Okay. And I can make a spectral sequence such that differential prolongs one antenna, makes antenna longer. So for example, filtration, I make filtration on number of edges that are not in the antennas. Okay. Therefore, in the spectral sequence, first differential will make number of edges that are not antennas the same. So that differential will just make one antenna longer.
I don't get that one, sorry.
So if you filter like this, the only thing that the differential will see is it will ignore everything that increases the edges outside of the antenna. So the only thing it can do is increase the length of the antenna. Because fix is the ephemeral edges.
Something about the edges?
Yes,
That's not meant to decrease, and that's
so when you take it to filtration, you don't see any part of the differential that goes into those deeper into filtration.
So if I have graph here with antenna and another antenna, differential can split this and can split this. So if differential doesn't act on antennas, it will add a new edge which is not an antenna.
So it will go to the further filter.
A further filter.
Which equality are you improving? The second equality or the first equality?
I mean, it's the same.
Is this improved?
Yes. I mean, this here is just that pole. So that this exists here, and if a tadpole is not free, I will kill it later by some spectral sequence. Yes. Okay, so do you believe me that here I can make spectral sequence on the number of edges which are not antennas, and then the first differential will be just part which extends one antenna. Okay, so D0 will not change this, but will do this. And this antenna cannot be extended because I will, it will be 0. So only odd antennas are extended, even antennas are 0. Because if I extend here and extend here, this will cancel. And therefore,
and that's why it's close to 0.
I mean, it has to pass square to 0 if
No,
it's
I know, but
part
also
of difference.
Because once it becomes even, you can't extend it.
Yes, okay, yes, yes. Okay, and therefore I can define homotopy, which contracts even antennas by 1. Okay. And now you can.
I don't understand. So you say that the differential can only.
No, this doesn't go here, but here plus. I mean the same thing, whatever. But
Anyway, so if I would have, say, if I would have another, if I would for my antenna, I have another component which has, let's say, 3 extension points.
yes, it will go to 4. Differential will make it 4. So this differential will
Okay.
Go
now
to
also take one with
4.
1. Additionally, so then I will get
plus
okay. I see.
the 1 extended to 2, and this stays. So here is then this one. And if I define this H such that it shrinks odd even antennas, you can see that DH plus HD is number of antennas times identity. And you can take, so complex cannot make or destroy antennas. So the complex with antennas is a subcomplex. And the complex
Create antennas.
Yeah.
You cannot initiate them. Then you can
Yeah. So full graph complex con is full graph complex con 1. This is with at least one antenna plus FGC con greater than or without antennas. And these are subcomplexes, and this complex is direct sum of these two.
Sorry, I didn't get what are the indices here?
The one with antennas and without the one without.
This is with antennas, and this is without antennas.
What is the index for?
Connected.
No, the index for 1 and 2.
Superscript.
Superscript. 1 means there is something one-valent.
Ah, okay.
And greater than or equal to 2 means everything is at least 2-valent.
Okay.
Whatever you can choose. Okay, so because this is not 0 here, homology of this with at least one antenna is 0. Therefore, homology of this is exactly only homology of this.
Wait, once again. The bottom part.
Homology of this is 0. This is acyclic.
Which has to be proved separately, I guess.
No, that's this proof.
Yeah, this is the part with antennas. You
Ah,
have
yeah,
antennas.
yeah, yeah.
Part of antennas, number of antennas is not 0. Therefore, if I have this,
Okay.
it's acyclic.
So if you apply to a cycle, one of the two DH plus HD, the H plus HD will disappear, and you will have that the thing is DH of somebody.
Yes.
Yes.
Okay, so on homology, I don't have this part. I have only this part. Now we continue with this. No, we are not on the second page.
We just take the homology.
Yeah, we're still on the 0th page. But I mean, if the homology is 0.
On this of this complex, on this complex, which has at least one antenna, I make a spectral sequence such that the first differential extends one antenna. And I prove that homology of this first differential is 0. Therefore, on the second page, I have all zeros.
So you have in the second page, there's no more antennas.
Sorry?
There's no more antennas.
Yes.
That's what, yeah.
Yes, then okay. Okay, now this full graph complex con this equals full graph complex con greater than equal to 2p for proper plus loops. Where this here are loops this looks like this, where everything is two-valent. And here there is at least something what's more than two-valent. I call this like this. And you easily see that both are subcomplexes. Loop, differential from loop makes loop. Differential from this cannot destroy the more valent vertex. Homology of loops is exactly this. Okay, if I put tadpoles, it's 1. If you not tadpoles, J congruent to 1 mod 4. It's clear because in loops everything is 0 except every fourth element, so homology has to be that. Differential is always 0. And this is just a degree shift you calculate. So that's how in the theorem we came to that part. So that's this part.
Looking at conversions, I mean, the spectral sequence, we don't consider it anymore? Or what?
We don't. No, we don't.
So we have used it only to talk about the first graded.
No, we killed with that spectral sequences. We proved that we can forget about antennas.
But we haven't checked that it was converging or whatever. We just concentrated on the first D0. What happened for the rest of
No,
it is convergent.
And the rest you don't care, because first you do the splitting, then you only apply the spectral sequence to this sum.
I mean, you wonder whether spectral sequence converges rightly to a homology.
I know. My question is why did we not compute all the pages? Why did we do only the first?
But if the first page is 0, then all the other pages are 0.
But the first page is 0, but only on the first graded component on F1 mod F2, or there are other.
But as I said, by general arguments, if you have, you know that.
No, it's not first order. Every order is 0. Because on every order, if we have at least one antenna.
No, but you could have other guys which have no antennas, right?
Yes, but I didn't kill it. I proved that this is a cyclic.
Yeah, so
I didn't prove anything about this.
Okay, and you don't care about the one on the right through spectral sequence. You use other tools.
Yes.
Okay.
So I used spectral sequence tool to compute that this is a cyclic. I didn't do to this anything yet. Now I am proving what's this, and this is this plus this. Now homology of loops I know. Now just need to prove that homology of this is homology of graph GC. And we are done. Up to tadpoles. So this here have a, let's call it skeleton. Skeleton is of a graph with only 3 or more valent vertices there. For example, skeleton of this graph is this, where this is. Now we think of this as an edge, more complicated
so
edge.
you eliminate every vertex with valence less than 3.
I don't eliminate, but I think as this is a vertex and this is a vertex and this is no more vertex, but this is an edge of length 2.
Sorry, why the one on the right is not also?
Sorry?
I mean, what's different between the one on the top and the one on the right?
Yeah, the rightmost vertex is also.
Oh, okay, yes.
valent.
Yeah, because otherwise you really get into trouble. Because if you take this original, you should kill the 2 rightmost edges.
No,
But then you get the loop back, right?
yeah.
Okay. So, you
So
get,
what was
vertex
drawn
with-
here would be
vertex with
this.
full loop, yes.
Okay. And now, very similar to story with antennas. I make a spectral, okay, so this FGC con greater than or equal to 2 proper is GC. This doesn't have 2 valent vertices plus FGC con 2P. This has at least 1 2 valent vertex. This doesn't have 2 valent vertices, this has at least 1 2 valent vertices. Now I want to show that homology of this is 0, and I'm done. But it's very similar to antennas. I make a spectral sequence such that the first differential prolongs this number to 1 bigger. And it will only move even to odd. It can prolong only even things. 1 cannot be prolonged, and 3 cannot be prolonged. So only even things will be prolonged. So therefore, for example, so 3 cannot go to 4, it will go to 0. But that up, D0 will move it to 3. And same, I can have homotopy there, which makes odd edge of length at least 3, one shorter by 1, and D0H plus HD0 will be number of edges which are not simple, times identity. Therefore, homotopy of this is homotopy of this. This is cancelled. And now to kill tadpoles. Okay, tadpole, you can make a spectral sequence which moves tadpole such that first differential moves tadpole to this thing, and then you define H and you have the same story. I don't want to go to details.
And so,
But the same story works. Like this, if there is at least 1 tadpole, it's killed. Really? Okay. Thank you.